All right, third and final video. In this video, we are going to talk about porosity. And in this discussion of porosity, we're going to talk about what it is. We're going to do some calculations related to porosity. We're going to talk about pore sizes. There's three main pore sizes, and they have specific properties associated with each one. And then we're going to summarize everything together. That is bulk density, particle density, and porosity to bring it all together, full circle. Okay, so just a little bit of background about porosity and what it is. So here we're looking at a clay soil with granular structure. And here we're looking at a sandy soil that we could call it single grained, right? Our single grains have about the same size as our clay soil that has the granular structure. The difference is that single grain soil is solid particles, right? Whereas our granular clay soil has these granules that are composed of a bunch of tiny clay particles. And therefore, since they're not solid, since these are not solid, there's pore spaces inside those structures. So when water gets into these two soils, water in the clay granular soil can go between the granules, but it can also go inside, right? Whereas for the sandy soil that's single grain, the only place that water can go is in between the particles. And so if I ask you this question, which soil has a higher porosity? Of course, you're going to say soil A, right? The clay soil with granular structure. And then this one's like super easy. But if I ask you this question, which soil has the sandy texture? It's, of course, that one right there, right? And similarly, if we move on and I talk to you about pore space now, hang on a second here. Pause that sucker. Okay, so when we talk about what pore space is or what porosity is, we're just interested in the volume or the space that the pores take up relative to the entire soil volume. So there's two ways that we can calculate porosity, right? One way is this way, and this way is called the direct method for determination of porosity. And all that it is the volume of pores divided by the total soil volume, and we multiply that by 100%. So I'm going to just rewrite it here. Percent P equals the volume of pores, and usually the units that we look at are cubic centimeters, divided by the total soil volume. The units that we look at there are cubic centimeters also, total soil volume. We multiply that by 100%. And this is a determination of porosity. And as I said, this is the direct method for determination of porosity. The other method that we can use to determine porosity, which turns out to give us the same value, is called the indirect method. So this formula right here is indirect. And just so we're clear, I'll just rewrite it again. Percent porosity, indirect method. We're still calculating the same thing, just a different formula. It is 1 minus a soil's bulk density divided by its particle density times 100%. So you'd use this formula if you didn't have the total soil volume, or if you didn't have the volume of pores, then you could do this one. Okay, so let's go through an example. So here is the example that we've been working on all along, and we're going to calculate the porosity both ways, direct and indirect formula. So percent P direct, right, is the volume of pores. The volume of pores is given here. That's 40 cubic centimeters. Divided by the total soil volume, which is given down here. That's 80 cubic centimeters. So it's the volume of pores divided by the total soil volume times 100%. And of course, it's 50%. Simple, easy, painless. So this is the same soil that we looked at before. And this soil, we know from before, had a bulk density of 1.33 grams per cubic centimeter. And if you don't believe me, you can calculate it. And it had a particle density of 2.65 grams per cubic centimeter. So we're going to calculate the porosity using the indirect formula. And the indirect formula is just 1 minus the soil's bulk density, which is 1.33 grams per cubic centimeter, divided by the particle density, 2.65 grams per cubic centimeter. Multiply that whole thing by 100%. And if you do the math, which I'm sure you will, you have 50%. Okay, so it's just two different tools that we can use to calculate a soil's porosity. Now, if we go back to this right here, and over here, we were talking about the things that influence bulk density, particle density, and now we're going to talk about porosity. Percent P is porosity. So it says that bulk density is influenced by texture, structure, percent organic matter, content, degree of compaction. And so is porosity, right? Particle density is only influenced by the soil mineralogy. So texture, structure, percent organic matter, and degree of compaction. And since bulk density and porosity are influenced by the same things, we need to talk about their relationship, right? And they have a beautiful relationship. Like if I was going to describe the relationship, I don't know, between me and my wife, I'd also say that that's a beautiful relationship. But this one, bulk density, how is bulk density and porosity related? So bulk density, actually, let's come back to that, okay? So let's go, no, let's go here again. We're going to go down here to get this started. So here we have the soils that we were working with before: loam granular, clay loam granular, sandy loam granular. And we know that the loam granular, the ideal soil, which has a bulk density of 1.33, particle density of 2.65, has a porosity equal to, you said it, 50%. And looking at the clay loam granular, we know that the porosity has got to be higher than 50% because the pore spaces take up more actual volume than in the loam granular. So in this case, the porosity is going to equal 55%. And the way that I actually calculated these, but before I started this, I used the indirect method. And if we go to the sandy loam granular, which has a bulk density of 1.5, particle density of 2.65, it's got to have a lower porosity than any of the other two soils because its bulk density is the highest. So in this case, the porosity is 43%. So then the relationship between bulk density and porosity, take a look here, right? This value here and that value, and then this value here and that value, and then this value here and that value. So what is the relationship, right? And I'm just going to write it down here. The relationship between bulk density and porosity is inverse. So bulk density and porosity are inversely related. All that means is that if one is high, the other is low. One is low, the other is high. So if you have a high bulk density, what that means is that you're going to have a low porosity, right? If you have a low bulk density, that means that you will have a high porosity. And every time when we're talking about this, think about and always go back to our loam granular structure, right? Which looks like this. Ideal bulk density and porosity for the growth of most things. So solids, pores, this is our loam granular. Always compare every single soil to this one, right? Use this one as like your standard and think about what a sandy soil that might have granular structure is compared to that one, or a clay loam soil that's compacted, okay? So back to this now. So here is bulk density. And the question that I'm asking at the bottom of this slide is what factors influence soil bulk density? And you know, right? Texture, structure, percent organic matter, and degree of compaction. If we talk about particle density, right? What factors influence particle density? It is soil mineralogy, and that's it. There it is, soil mineralogy, that's it. And if we talk about the factors that influence porosity, same ones as bulk density. Texture, structure, degree of compaction, percent organic matter content. Simple, easy, painless, enjoyable. It's a beautiful relationship. Okay. All right. Next thing we're going to talk about is pore size. Okay. We're going to talk about macropores, mesopores, and micropores. And in this discussion, we're going to talk about a few things. One, we're going to talk about how big these pores are. We're going to talk about the types of soils where we find these pore sizes. And we're going to talk about sort of what they do in a soil. Okay. So again, how big they are, the types of soils that we're going to find them. Usually I'm talking about texture and structure, and then what they're good for. Okay. So here they are. Macropores are greater than 0.08 millimeters in diameter, right? So that's still pretty tiny, but macropores are classified as that. Mesopores are between 0.08 and 0.03, and micropores are less than that. All right, so let's break it down now. Let's talk about macropores. Macropores are mostly found in sandy soils, and they're found in like clay and loamy soils with good structure. And what I mean by that is that the macropores are found between the aggregates or between the structures. Okay, so of course they're found in sandy soils, and they're also found in clay and loamy soils or soils with more clay in them. But the macropores in these are between the structures. Okay. What do they do, or what are they good for? These are the pores that are responsible for drainage in a soil, right? Drainage and aeration, right? What I mean by aeration is just the free and easy movement of gases in and through a soil. So the macropores do that, all right? And it's important, right, for the growth of every plant, right, to have good drainage and good aeration or good exchange of gases. Next one is the mesopores. And the mesopores are going to be like found largely in loamy and silty soils. And they're usually found like inside soil structures. Okay, largely there. Sometimes like on the outside of soil structures, but largely on the inside of soil structures. And here is the key thing that the mesopores are responsible for. And we're going to talk more about this, and maybe it's more appropriate to say we're going to drink more deeply about this cup later, but they are largely responsible for what we call plant available water. So the water in the soil that is available to plants is largely held in the mesopores. And we oftentimes give this the acronym PAW. Okay, we'll come back to that later when we talk about soil water. And lastly, the micropores, tiny. These are mostly found in clay soils. And they're inside aggregates, right? They're inside aggregates. And these are responsible for long-term water storage. and water holding in a soil. And sometimes the micropores are so small that there's so much specific surface area of soil particles that make up the microporosity in the soil that those soil particles hold on to the water too tightly for the plants to get. So the plants can't get all the microporosity or the micropore water. I need to go back and talk about how compaction influences each of these. So let's go back just real quick to our discussion of macropores. So compaction destroys our macropores. So the first kind of pores to be removed from a soil upon compaction are these. And so essentially, when you compact a soil, you remove the soil's ability to drain water easily and actually to move around gases. Compaction destroys them. Okay. For plant available water, or for the mesopores, right? We're talking about mesopores in this slide right here. Compaction destroys the mesopores. And lastly, for our micropores, right? We're talking about the micropores on this slide. Compaction, most of the time, has a pretty small effect on our micropores, unless the soil is wet. The soil is wet, then the micropores can be destroyed, okay? When soil is wet or saturated, all right, compaction can destroy them. And so that's why, like, I don't know if you've ever seen this, but at a construction site where they might be preparing a soil to put a foundation upon it, something that they do in large scale projects is that they'll put like something heavy over the soil, some kind of compacting device over the soil, like some kind of roller or really heavy kind of tractor, and they'll get the soil wet and then run the tractor over it. And what the water's doing is acting as a lubricant between the soil particles, so that when you put something heavy on top of it, it destroys those pores. So when soil is saturated, compaction can destroy the micropores. All right. So last thing that we're going to do is we're going to summarize everything. And we're going to fill in this table here. Okay. So we have coarse texture, fine texture, and a compacted soil. And essentially that's going to be related to sand, clay, and then it could be any. And then for structure, we're going to say what is a reasonable structure associated with these. For sandy soil, single grained or granular. For the clay soil, granular or blocky, and the compacted soil will be platy or massive. So then what we want to do is predict what is going to be the bulk density of these, what's going to be the porosity of these. And we know that bulk density and porosity are inversely related, right? So those are some typical bulk densities, right, for these different soils. And you should, as we're thinking about these and writing them down, should be able to draw a simple but elegant soil pie chart for each of those. Okay, porosity we know is inversely related to bulk density. So the porosity is going to manifest that way, right? So for 1.5 bulk density, porosity is going to be low, 43%. For a bulk density of 2.1, the porosity is super low, right? Pore size. So think about what is the typical pore size for a sandy soil. You guessed it. It's macropores, right? For a clay soil, it's macropores between the structures and micropores inside the structures, right? And for a compacted soil, very few micropores, right? The porosity has been destroyed, and the only pores that are going to be left are the micropores. Aeration. What does aeration have to do with? You tell me. What is it? Macroporosity. So the soils that have macropores have high aeration. So that's why for a sandy soil, you got high aeration. For a clay soil with granular or blocky structure, you have relatively low aeration, but if you have good structure, right? If the soil's got good structure, then you'll have some medium amount of aeration. And for a compacted soil, because all you have is microporosity, very low. Okay. Water movement. How does water move quickly through a soil? Macropore space. So soils with macropores, water moves quick. So in a sandy soil, it's fast. In a clay soil with granular structure or blocky structure is fast and then slow. We're going to talk about and come back to that in just a minute. And then, of course, in a compacted soil that's got player massive condition, it's very slow. So let's talk about this, fast and slow. So initially, right, if we go here, if we talk about this as clay kind of granular structure, so water is going to move super fast, right, through there, super fast through here, super fast through here, right, between the granules. So that is accounting for the fast movement of water. But over time, right, water is going to start moving inside the granules. And it's gonna, as it gets in there, it's gonna act as a lubricant between the soil particles that form those granules, and it's gonna weaken that structure. So it's going to kind of cause it to collapse. And when it collapses, the collapsed particles are going to fill in the pores. And when you fill in those pores, essentially you're going to stop the movement of water. So that's why the water movement is fast and then it's slow. Okay, makes sense, right? Water holding capacity. What is the property of the soil that lends itself to water holding capacity and high water holding capacity? One is porosity, but two is microporosity, right? So sandy, low, clay, high, and a compacted soil, of course, there's very low pores, so it's very low. And then what is the particle density of these soils? Let's assume that they're forming in a temperate region soil, which is mostly composed of quartz. So all the same, right? 2.65 grams per cubic centimeter for each of them. That is it for our third and final video. And it'll be important for you to watch these. If you need to, you can rewatch them. On Wednesday, what we're going to talk about, or in our next class, what we're going to talk about is water in a soil. And I'm also going to assign a homework assignment related to calculations of bulk density, porosity, and particle density. And it should be pretty good and interesting stuff. All right, thank you for your attention and for watching. I look forward to seeing you in our next class.